I'm going to move on to our next speaker. We have with us Dr. Sarah Baatout, is head of the radiobiology unit at the Belgian Nuclear Research Center. This unit evaluates the potential risks of ionizing radiation on health and conducts radiation risk assessments for occupational, accidental, medical, or space radiation exposure through high throughput molecular and cellular technologies. Please welcome Dr. Baatout, who will share with us how to protect astronauts from radiation.
So it's really a pleasure to be here. I don't know if you can see my screen.
Yes, we can.
Okay, this is wonderful. So I'm really pleased to join this incredible conference and to join this panel of presentations and speakers. And I would like also especially thank Robert Zubrin and Lucinda and James for the immense work that has been put in the preparation of this amazing conference. I'm coming from Belgium, and I will present a little bit the point of view, the European point of view, but I think it shares really a lot in common with the NASA way and the other international agencies related to radiation protection. So I'm very pleased to come and to present. And as you can see also, I'm representing Mars Society Belgium. We have a very strong and active society in Belgium, and I'm very pleased that we can present today. So first, let me introduce what we do exactly at the Belgian Nuclear Research Center in Mol, located not so far from Brussels. Basically, Brussels is the capital of Europe. It's not that far, 1 hour driving. And basically, we are focusing on 3 different aspects related to space research, which are very much aligned with supporting productive, healthy human space exploration of the solar system. In our case, we will put the accent, especially during this presentation, on the word human. So how to prepare and how to protect astronauts in view of long-term space mission. Our expertise is pretty long in terms of space experiments, as you will see, and is mainly divided into the study of radiation inside and outside space vehicles, and this is done through our physicists and dosimetrists. We also have a very strong research group in microbiology looking at life support and producing food for long-term mission, and especially for the moon and for Mars. And then my group, the group of radiobiology, is really studying the impact of cosmic radiation and radiation in general on health. And on top of that, because we are, the Belgian Nuclear Research Center is more than 60 years old, we have a very strong knowledge and expertise on radiation resistance of any type of material. So that could be useful for space exploration, and also working on radiation sources for space propulsion, where I think Americans are much further away than Europeans. But I think where some alignment would be very useful. So at the day of today, we are almost 60 years of space missions, from the first orbit of Yuri Gagarin in 1961 to now. We are preparing missions that are longer and longer. For the moment, on the International Space Station, on the ISS, missions are about 6 months to sometimes up to a year. But we are heading towards longer and longer mission to the moon and to Mars. And we know that if we speak again about the human aspects and the impact on human health, that space flights have an important impact on the human body. And we know certainly that the different parts of the body react differently to the longer the duration and the longer the impact on certain types of cells and certain systems that I will speak more into detail. But we are heading towards longer space missions where risks will be increased. We are in this big endeavor. It's a universal endeavor, which is the Deep Space Gateway, which would be the first human spaceship to explore solar system, the most distant human space missions ever attempted and a testing ground for challenges of long duration human missions in deep space. But there is a strong showstopper, and it's radiation, cosmic radiation, ionizing radiation in general. Ionizing radiation, space radiation, is the #1 risk to astronaut health beyond low Earth orbit. And as we look at the MHRPE, which is the Multilateral Human Research Panel for Exploration, which is really a very important international panel from the Canadian, the American, the Japanese, Russians, but also European, in order to estimate the different risks that could be encountered by astronauts. We see that if we look at here at this map, at the bottom of this table, you can see that radiation, and certainly radiation to go to Mars, would be really the first one of the main risks, as you can see, as shown in red. As shown in red are the very high risks with high consequences, and where we really absolutely need mitigation. And this is what radiation protectionists and researchers like my group are currently doing, but not only in Belgium, but in many places in the world. As mentioned earlier, I think by Robert in his introductory talk, of course, on Earth, we are very much protected. We are kind of cocooned on Earth thanks to our magnetospheres and our atmosphere. About 99.9% of radiation is stopped. So the dose of radiation is pretty low, as you can see here on this dose expressed in millisievert, and if you compare that to other space missions. So on Earth, the population receives on average about 1 millisievert per year. And if you compare that to an ISS mission, where we have put our dosimeters and we're still having and measuring regularly the dosimetry and the doses of irradiation, we are about 150 times higher doses of irradiation. But going to the moon and going to Mars, as you can see, we increase of a factor of 300 from in comparison with the Earth, and about what for the moon, and about 1,000 for a full Mars mission. So the dose of irradiation is going to be very much higher, but not only the dose, but also the quality, the composition of this radiation will be very different from Earth and much more damageable for the cells, as I will explain a little bit more into detail. So again here, just in terms of doses, on the International Space Station, we have about 150, 160 times more radiation than on Earth. Of course, radiation doses are mission specific. They depend on the destination, on the duration, on the vehicle and the habitat, because that can provide a different dose of radiation inside the habitat. And of course, they are very dependent on the solar conditions. On the moon, if you look at a lunar mission of about a year, you would have about 300 times, 300 to 400 times higher doses in total than on Earth. And then going to Mars and back about 1,000 times more than on Earth. But what are these space radiations? In fact, there are three main categories, I would say. You have first the solar wind. The solar wind is a continuous low energy flux. It represents a low hazard. So for us, it's not such a big issue. It's a continuous flux, but it can be stopped. It can be stopped by the vehicle, by the coating of and the coat of the vehicle. So for us, the solar wind is not such a big issue. However, where we are much more concerned are the solar particle events. Of course, these are really a very high energy protons flux, which is intermittent, that can last for a day or two, and it's extremely hazardous. And also the galactic cosmic rays that are composed of very high energy protons, also alpha particles, and also heavy ions. This is also a continuous flux, and it's hazardous, and for which we really need to find mitigation. So different ways that I will go more into detail to explain to you. What we have to take into account also are the secondary radiations. And these secondary radiations are produced by the primary radiations that are of solar or cosmic origins, and that interact with the nuclei, with the material of the spacecraft, and generate, or with the human body, and can generate secondary particles. And these secondary particles can be really a myriad, hundreds of thousands from one particle. So that can generate secondary damage and even more difficult damage for the cells inside the human body to repair. Right now, the ISS, the International Space Station, is really critical to mitigate Mars mission, human health and performance risks. So a lot of the research is performed on board of the International Space Station. For what concerns the Belgian Nuclear Research Center, we are measuring continuously those doses and the doses of radiation in and outside the ISS. We're also measuring the health of astronauts, the immune response and the radiation sensitivity of astronauts and cosmonauts. And we're also participating in what we call the ESA, European Space Agency, MELISA program, which is the life support program, one of the main life support program from ESA. Radiation doses on the ISS is about 150 times. We perform radiation monitoring and characterization on the ISS in order to better understand space radiation and how it penetrates the International Space Station walls through active and passive detectors to map inside the ISS and inside the various modules the radiation doses. And for that, we change every 6 months the different detectors that come back on Earth, and then we send some new detectors in order to have a continuous monitoring. And that helps us to create a complete picture of space radiation. And it's very helpful, and this is a collaboration we have currently with the German Space Agency. We have been very lucky. Belgium had so far 2 astronauts that flew to space. We have here our second astronaut, Frank de Wien, a very strong supporter of our research. And he's placing here, as you can see, some detectors inside the European Columbus module. So all the little red dots that you can see are our detectors on the Columbus modules. In case of solar flares, there is some good radiation shielding that can be provided inside the ISS. That's in 3 different places where the astronauts can go and protect and get protected for a certain amount of time during the time of the solar flares, during the time of this, which is needed. And as you can see in the middle of the ISS map, the water wall, the water container is a very big source of protection for the astronauts. Let's move now to the moon. Moon with about 300, 400 times higher doses of radiation than on Earth, with a very interesting international moon village program in which humans and robots would work together on different operations and on different research projects, also in astronomy and on the lunar surface, for which a moon village will be built. The moon is the archive of the Earth's early history. There is no magnetosphere, no general atmosphere to protect us. So there is no real protection from harmful space radiation. So very important as a testing platform, and also can be taken as a springboard or a testing ground before going to Mars. And going to the moon, staying on the moon, having a moon village, it also means that there will be many more extravehicular activities. If we compare, for example, to the Apollo program, where you had in total about 20 extravehicular activities during the entire Apollo program, what is expected on the future lunar program is about 70, 80 lunar EVAs during the 6 months mission that the astronauts would stay inside on the surface of the moon. So a particular attention needs to be given to the spacesuit because it will be the kind of only protection for the astronauts when they go on EVAs. So the spacesuit need to be resistant to abrasion of reactive chemical dust, to UV, to temperature, to oxygen, and to weight. It also needs to provide some possibilities for walking. So it needs to be kind of a flexible material and elastic material. And at SCKCEN, so at the Belgian Nuclear Research Center, we are working, amongst others, on different types of spacesuits. And then going to Mars with doses very roughly about 1,000 times if you count the way to go and back, with Mars being the most similar planet to the Earth, that would help us to understand, as already mentioned by Robert, whether life existed elsewhere in the universe, which is really a fundamental question for humanity. We know that it was once full of water and warmer, and it provides a habitable environment. What are the space radiation health risks? We know that they are quite numerous. First, the induction of a higher risk of for developing cancer. This is what we called carcinogenesis. So space radiation exposure may increase cancer morbidity or cancer mortality risk in astronauts. But not only that, also other tissues of the body, like the central nervous system, like the cardiovascular system, or like the lens, can be also and are known to be quite sensitive to radiation. Where it's reported that high level of radiation can induce acute or late changes in cognition, in motor function, behavior, and mood, or neurological disorders. For cardiovascular disease, it can increase the risk of stroke and other cardiovascular impairments, and induce also accelerated aging in different tissues, and also the immune dysfunction. In case of very high doses, like in solar particle events and without any protection, you could develop what we call the acute radiation syndrome, which is a combination of different types of symptoms like nausea, vomiting or anorexia, fatigue, skin reddening, depletion of the bone marrow and of the blood forming organs. And space radiation is quite also complex because also of the biology behind it, because the quality, so the composition of space radiation, this galactic cosmic radiation, is very different than on Earth with what we know. So it also provides a very densely ionizing track, as you can see on the right-hand side of the pictures, where you see in blue the cells of a human body, and in green this track. And this track means the DNA damage induced inside these cells at the level of the biomolecules, at the level of the cells, as we can see, but also at the level, it can be extrapolated to the tissue level and the whole organisms. And so this space radiation provide a distinct pattern of DNA damage and also a distinct profile of oxidative damage and of repair duration. And so it's very important to understand, to characterize this type of damage. And so far, we don't have that much information on human data. And we know that animal studies as cellular models are very important to be placed in simulated space conditions to understand and to gain new scientific knowledge in order to be able to counteract, to mitigate this impact. And what we also need to understand better is that there might be some potential and additive effects or synergetic effects of the different space stressors, like microgravity, for example, or other space flight factors. This is just a snapshot for you of the ESA scientific space programs. This is a Science in Space Environment Roadmap from 2016, and a big effort is placed for the moment. All the experts in Europe are updating this roadmap. And so we hope in 2021 to have an updated roadmap for our science and future science strategy. And as you can see on the biological effects, we want to understand better What is the radiation response of the cells, the radiation sensitivity of the different parts of the body, what are the molecular underlying mechanisms is very crucial to understand. We need to really be able to better assess the radiation risk and to develop countermeasures. So this is really essential. On the left-hand side, you see that the whole body doesn't have the same radiation sensitivity all through, and that there are some parts of the body that are quite sensitive to radiation, in particular the lungs, the breast, the intestine, the stomach. We know see the bone marrow and the reproductive organs. So the risks is increasing. The higher the doses, the longer the duration of the mission. As we can see, we increase very much the risk by going to Mars and the risk of developing cancer. Not everyone is equal when we look at radiation response. Amongst us, amongst the population, but also amongst astronauts, some of them will develop a very high radiation response and will be considered as radiation sensitive, and some astronauts are more radiation resistant. And these kind of studies are also performed at the Belgian Nuclear Research Center on astronauts in order to provide their radiation sensitivity monitoring before and after they fly to the ISS. And sensitivity to radiation varies with age. We don't keep the same sensitivity all through our life. We are much more radiation sensitive at the fetal stage, at the embryonic and fetal stage, as you can see on the left-hand side, and then the older we get and the lower the sensitivity. So this is also quite important for monitoring and determining the best radiation sensitivity age for long-term mission to Mars. And as you can see, when you reach an age of 30, around 50 years old, that's where your sensitivity also starts to decrease, and that can be quite interesting to target also this age for Mars mission. Sensitivity is also different between females and males, where you can see here the risk of radiation-induced death, the REID, which is gender and age dependent, which is larger for females than for males, and which is decreasing with age. What we also cruelly need still now, it's really an harmonization at the level of all the international space agencies in order to determine what are the tolerated thresholds that for astronauts, because this is a universal endeavor to go to the moon and to go to Mars, but still, as you can see, the different agencies have got different tolerated thresholds. And there is a working group taking place right now in order to discuss and to come up with a solution that would be adapted for all the international space agencies in a universally harmonized way. Important as well is the development of precision medicine in astronauts, and certainly in terms of radiation protection, to be able to know beforehand what is the precise radiation
5-minute warning
of the astronauts, and to adapt their program of missions depending on their radiation sensitivity. There are different biomarkers of radiation sensitivity, biomarkers of exposure, of susceptibility, biomarkers of late effects of radiation, and persistent effects. I just would like to mention some few experiments that we are performing. First, the monitoring of radiation sensitivity in space, where we have the advantage to get access to blood of astronauts before they go to a mission on the ISS and when they come back, and in order to monitor if their radiation sensitivity has changed. You have been probably following a very interesting talk on Thursday from Eline Ratzbach from my group, and she's been talking about skin and wound in space. So if you would like to listen to this talk, if you've not done it, I would like to invite you to listen to the skin. If you are particularly interested in the skin sensitivity, to listen to this talk. We also sent through SpaceX 8 some experiments on growing blood vessels in space. And we're also currently performing some studies on brain cells in space. What is also very important is to study the microbiome and how the gut microbiome is changing in the space environment. And for that, we investigate how the microbiome composition is altered in space environment and how this decrease of diversity in the gut microbiome is taking place. And next month, we are very lucky also to send some very extremophiles, some interesting beasts, the rotifers, that are going to give us, for the second time, some more information about how come these organisms are so radiation resistant and what can we use from this information in order to make even astronauts more, eventually, more radiation resistant for long-term missions. I just had also the privilege to go to Antarctica, as you can see here on the Princess Elizabeth Station, which is a very interesting space analog where we can really monitor also different aspects of health that really help us to understand even better the impact of long-term missions on the human health. How can we improve radiation resistance to astronauts? I would like to invite you to one of our latest publications published and freely accessible in OncoTarget, where we go into detail into how to improve shielding, how to medically be able to select radiation resistant astronauts, how to and what type of radio protectors we have developed so far, what type of biomarkers, how can we decrease the metabolism, and how can we work with regenerative technologies in order to make and improve radiation resistance in astronauts. So astronauts are radiation workers. So for that, we need to find the best acceptable level of radiation exposure. This is what we call the ALARA principle, as low as reasonably achievable. And so we need to implement real-time radiological support, understand and minimize exposure, understand the effects of space radiation, and develop the proper technologies for that. Let's not forget that space radiation research benefits to patients on Earth and, amongst others, benefit to cancer research because there is really a strong link into development of cancer research and the best protocols for radiotherapy and space radiation research. If you are interested by this field of research, I just would like to invite you to listen to the TED conference that was recorded a few months ago. And if you would like to have more information into the research that we have performed, come and enjoy SEKCN. I just would like also to reach out to the young generation, to the students. If you're interested in this topic, just contact us. Don't be shy. We are there for you. And I would like to acknowledge and the people from the Belgian Nuclear Research Center, as well as ESA, as well as my agency in Belgium, BELSPO, the International Polar Foundation, the Mars Society Belgium, and some of my main collaborators, as you can see, from the different universities in Europe. And with that, I thank you very, very much for your attention.
Thank you so much. We are now going to, we ran out of time for Q&A, and we're now going to go back to Dr. Zubrin for an announcement. Thank you so much.